Welcome to our Chapter 14 lecture video. This week we're going to be talking about acids and bases. We've talked about these already in Chapter 7, but we're going to get a little bit more into the details. So parts of this can be broken up into conceptuals, and then other parts can be broken up into calculations. So these first three topics, the properties, the definitions, and what are called conjugate pairs are kind of just conceptually. We want to understand things that define or relate to what acids and bases are generically. And then we can do some calculations with acids and bases. You should be becoming comfortable with the titration calculations because this is what our lab for the past 2 weeks has been on. And then pH and pOH is something that's a little bit more familiar to everyday people. We don't typically use pOH, but we use pH a lot. The pH of lemon juice is like 1. We'll talk about these and how we can use them to do specific calculations. But the first thing is we want to talk a little bit about the properties of acids and bases. So whenever you taste something that we call acidic, it has that sour taste. This is one of the cornerstones of what an acid is. This is because in most cases, and in all the cases that we'll talk about, acids are things that produce H plus ions. And so we'll have a couple definitions. We'll have the Arrhenius definition, the Bronsted definition. There's also a Lewis definition, but the Lewis definition is more useful for organic chemistry and is just more complicated than what we need for our general and our introductory chemistry. So we're going to focus on the Bronsted definition, which looks as hydrogen ions as protons. If something donates a proton, it's an acid. So if it gives up H+, it's going to be an acid. Gives us this sour flavor. If it accepts H+, then it's going to be a base. We'll talk on this a little bit more. But in general, acids are sour. They dissolve metals. This is not the same way that water dissolves sodium chloride or some other ionic polar compound. Acids actually react with metals to form hydrogen gas and some, metal salt species. But another way we can look at them is indicators. So we've worked a little bit with indicators. Litmus paper is a very specific, cheap indicator that tells you whether something is acidic or basic. If we have blue litmus paper, we're testing for acids. If we have red litmus paper, we're testing for bases. They turn the opposite colors. Blue litmus paper turns red in the presence of acid. Red litmus paper turns blue in the presence of base. So HCl is one of our go-to acids. It's probably the most common small acid or binary acid that's only composed of two things. Any hydro acid is hydrochloric, hydrofluoric, hydrobromic, hydroiodic. It's just hydrogen and the halide. Very common class of acids. We also have sulfuric acid. Sulfuric acid is the number one produced chemical in the world. We use it for all sorts of things. Here's a couple examples, but we also use it heavily in, the pharmaceutical and technical industries. So organic acids are typically these carboxylates. So you have carbon doubly bonded to oxygen, bonded to another oxygen singly that then has a hydrogen that it can donate. This is the ionizable proton or the acidic proton. These protons that are bonded to carbon are not acidic because there's not a big enough difference in electronegativity that we can ionize that hydrogen into H+ or into a proton. So vinegar, acetic acid is the acid in vinegar. Should know this from this past week's lab, but just to remind us. In general, the way our foods are acidic is not through mineral acids like hydrochloric or nitric acid. There can be traces of those, but predominantly it comes from these organic acids that contain carboxylic acids. Remember, C double bond O bonded to an OH group. So bases are going to have very opposite properties. So they taste bitter instead of sour. They have a slippery feel. And so this is, again, because of the reactivity of bases, just like acids dissolve metals because they react with them. Bases feel slippery because they react with the oils and skin on your hands. They also, like we had mentioned, turn red litmus paper blue. Blue is kind of our basic color. Pink or red is kind of our acidic color. So oftentimes when you're working with various cleaners, you'll feel slippery. This is because most cleaners are made from bases. All soaps are mildly basic. And so they actually react with the oils on your hand to do a saponification reaction. And essentially, soaps and bases just dissolve your skin and oils from your hand. Many bases contain nitrogen, and most biologically active molecules tend to be basic over acidic. Now, there's a whole bunch of biological implications about this that we don't really care, but in general, nitrogens tend to be the active molecule or active atom in a molecule. So caffeine has a whole bunch of nitrogens. We can also take other alkaloids, which are things that are composed by plants that have these very reactive or very, I guess I shouldn't say reactive, but very active nitrogens within the body. So there's a bunch of enzymes that can interact with the electrons on nitrogen. It causes a whole bunch of effects in the body that we're not going to really focus on, but in general, most medicines fall into this alkaloid classification. But they also fall into some poisons as well. So common bases, we've dealt with a few of them. Sodium hydroxide is one that we've definitely dealt with. Sodium bicarbonate is another one that we also commonly deal with, or that you've probably dealt with in your everyday lives. Unless you've worked on a farm or in a bakery, you probably don't work too much with sodium hydroxide, but it is an active ingredient in drain cleaners. So we'll acknowledge the Arrhenius definition. This was just the first definition of acids and bases that was generally accepted and usable. And so if something produces H plus in solution, it's called an Arrhenius acid. If something produces OH minus, this is called an Arrhenius base. We're going to focus on the Bronsted definition, which looks at an acid as a proton donor. If something donates a proton, it's going to produce H plus in solution. And a base is going to have a little bit different definition where it accepts a proton. OH minus or hydroxide can accept a proton to become water. Arrhenius looked at water and saw that two molecules of water can react to form H plus and OH minus, and he used this as the basis. It works for 90% of aqueous acids, but there are some that we'll point out that don't quite fall into this designation, so it's easier to use the Bronsted-Lowry definition. So, HCl produces H+. HCl would be considered an Arrhenius acid because it produces this H+. That H on HCl is ionizable. Because of that, we would call it an acid. In reality, what's actually happening is there's so much water relative to the acid or base that you're either going to form these hydronium species or the hydroxide species. If it's accepting the proton, it's going to accept a proton from water and create the hydroxide species. So hydronium and hydroxide are the foundation of Arrhenius acids and bases and really work as the foundation for all types of aqueous acid and base conditions. But there are some exceptions. So because there's so much water around that just statistically the ions are going to associate with water before they associate with the source of the ion. It's just a statistical happen. So we can look at the molecular formulas versus the structural formulas or the Lewis formulas. The Lewis formulas can be a little bit more tricky because you have to make a decision. Is what hydrogen's bound to a big enough difference in electronegativity that it can ionize? If it can hydrogen bond, it can ionize. So that's kind of your rule of thumb, is if it could be considered a hydrogen bond donor, it's also going to be potentially an acid because if it can hydrogen bond, it can also ionize that hydrogen to some degree. Whether it fully ionizes or partially ionizes is not going to be a discussion of this class. That just determines whether it's going to be a strong acid or a weak acid. When we do the molecular formulas, we offset the hydrogen. So this is why there's an exception when we have hydrogen bonded to carbon. We don't just do it purely on electronegativity. We put the hydrogen second. The ionizable hydrogens are, the cation, so to speak. The CHO2 is essentially the anion. So we give it that type of ionic treatment in this case. So Arrhenius bases are similar to Arrhenius acids, except for they produce OH minus instead of H plus. So if we take sodium hydroxide, our quintessential base, it fully ionizes and becomes OH minus and Na plus. Because OH minus is produced in solution, we could call this an Arrhenius base. It's also a Lewis base or a Bronsted base. Arrhenius is the lowest classification of acids and bases. Bronsted is the middle classification, which we're going to focus on. Lewis definition supersedes all, but is a little bit more complicated and looks at how electrons move rather than just the flow of protons. Following protons is a little bit easier. That's what we're going to focus on. So Arrhenius basically came up with this type of equilibrium. We call this the auto-ionization of water, but H plus and OH minus can either come together to form water, or we can look at the reverse reaction and say water decomposes to form H plus and OH minus. This process is called the auto-ionization of water or the autoprotolization of water. Depends on what textbook you're looking at. The more specific definition that we're going to focus on, you should know the Arrhenius definition, but if you can only remember one of them, remember the Bronsted-Lowry, which we shorthand to just the Bronsted definition. Lowry kind of gets left out of it, unfortunately, just how it goes. But we can consider acids things that donate a proton or H+. We can think of bases as things that accept a proton or H+. So this, definition came about 40 years later. It's just a little bit more widely applicable, and because of that, it gets more usage. Arrhenius still gets a lot of credit and love because there's equations named after him that you'll use in further chemistry classes. We're not going to do the mathematics of weak acids. We're going to treat everything like a strong acid. When things are strong acids or bases, they fully ionize. It makes the calculations much easier. You don't have to do, formulas and things like that. You just have to do your stoichiometry. So HCl, which we already defined as an Arrhenius acid, is also a Bronsted acid because it can donate a proton to something else. In this case, water is the Bronsted base. It's able to accept the proton and become hydronium. Ammonia is one of those common ones that we can't always use this case. We can use this as a Bronsted and an Arrhenius base, but there's often cases where if we're not dealing with water, if we react ammonia and HCl in the neat format or without water, you would get a Bronsted base reaction because we don't produce OH. In this case, ammonia is a Bronsted base and an Arrhenius base, but sometimes the Bronsted definition, especially with things like ammonia that aren't water-based, there's a nitrogen, there's no oxygens, so it's a little bit chemically different. Sometimes you get different byproducts out of it. And because of this, the Bronsted definition works just a bit better than the Arrhenius definition. So we mentioned how we have conjugates. The conjugate is what you get after you do a reaction. So when I have an acid, that acid reacts and then becomes a base. When the base reacts and accepts a proton, it now has an extra proton that it could donate to another base. Now, the conjugates are never as strong as the initial species. So a strong acid turns into a weak base. So NH3 is a, decent base. NH4 plus is a weak acid. Water is a very neutral acid. It has a pH of 7. Hydroxide is a very strong base. So your conjugates are always going to switch their behavior. If you come from a strong acid, you'll have a weak conjugate base. If I come from a weak acid, I'll have a strong conjugate base. So certain substances, depending on how many hydrogens and how many lone pairs they have, can act as both acids and bases. So we'll notice that depending on what we pair water with, sometimes it acts as an acid, sometimes it acts as a base. And so typically with things that we call amphoteric, if you react them with something that's more acidic than them, as the case with, hydrochloric acid in water, it can behave as a base. But if you react it with something that's more basic, like in the case with ammonia, water will act as the acid because ammonia is more basic than it. These are what we call amphoteric chemicals. They just can behave as both acids and base. This is kind of a weird term that we don't typically use to describe things. We just say something's an acid or a base or both, depending on the conditions. Here we have the reverse reaction of the previous reaction, and so just showing that the conjugates can then go on to do their own acid-base reaction. It's also important to note that NH3 ammonia can act as an acid or a base, but you need a little bit more extreme bases than you would with the case of water to make it into an acid or a base, but not as important. Just pointing out something that we might see in the future. So we've talked about conjugates. They're important in just how we communicate about things. It's not that, the conjugates are going to be super important to the reaction chemistry. It's just a way that we communicate. And so, whenever you have a base, you do a reaction, it's going to become the conjugate acid. If you have a base, or if you have an acid and you do a reaction, it's going to form a conjugate base. Acids turn into conjugate bases, bases turn into conjugate acids. It's just, a cycle. Just like we have redox cycles, we have acid-base cycles. So, just as we were saying before, here we have an acid-base reaction. Sulfuric acid is going to be the acid. The name kind of gives it away. Water is going to be the base. Once they react, you now have this bisulfate that is the conjugate base, and hydronium that is the conjugate acid. Now, sulfuric acid is a polyprotic acid. So technically, even though this is the conjugate base of sulfuric acid, it's still itself an acid that could go react with another molecule of base to form another conjugate base. That would then give us the sulfate conjugate base instead of the bisulfate conjugate base. Neutralization reactions are just a form of acid-base reactions. All neutralization reactions are acid-base reactions. Not all acid-base reactions are neutralization reactions. What makes a neutralization reaction is when we have an acid and base that comes together to form water and a salt. So if we take ammonium and hydrochloric acid, that will not be a neutralization reaction. It produces a salt, but it doesn't produce any water. And so Arrhenius acids and bases will always form neutralization reactions, whereas Bronsted bases and acids sometimes don't form neutralization reactions. We can use net ionic equations to kind of represent these neutralization reactions because, like I said, Arrhenius acids and bases will always do these neutralization reactions, so we can treat the acids as H plus and the bases as OH minus. Another type of reaction we see is when we have the sulfite or carbonate ions that we can have gas evolution reactions. So with the case of carbonate, we propose to leave as CO2, whereas with the sulfite polyatomics, we're poised to leave as SO2. So these are small, very stable molecules that can be broken down by an acid-base reaction. So lastly, we want to make sure that we're always balancing our chemical reactions. And so if we have one-to-one or monoprotic to monoprotic, we'll always have balanced stoichiometry. But in the case that we have a diprotic or polyprotic acid to a monoprotic base, most bases that we use are monoprotic. Sodium hydroxide can accept one proton as a base. Other things can be diprotic, so like calcium hydroxide is a diprotic base. It's not a very useful base because of solubility concerns, and so we tend to use monoprotic bases. Polyprotic acids are a little bit more common than polyprotic bases, and so typically the acid is what's going to determine whether you have to balance some, complex stoichiometry rather than just one-to-one ratios. In this case, HI is a monoprotic acid. Sodium hydroxide, monoprotic base, will do just a one-to-one neutralization reaction because both of these are definable as Arrhenius acids and Arrhenius bases. We had mentioned that acids dissolve metal. The reason for that is acids react with metals. So any hydrogen-based acid, so not a Lewis acid, we're not going to talk about Lewis acids, we're going to focus on Bronsted acids, which donate a proton. If you donate a proton to metals, you will create H2 and some metal salt. So you can do this for magnesium, you can do it for calcium, you can do it for iron, you can do it for pretty much any reactive metal. This doesn't work very well for the noble metals like platinum, palladium, gold, and silver. But if we treat gold with HCl, it does turn into gold chloride and gives off hydrogen gas. So these are just a couple metal reactions that we can do, very common ones. Iron, zinc, and magnesium all readily react with acids to form hydrogen gas and some metal salt. We can also do these similar type of reactions with metal oxides instead of just the metals. If I react a acid with a metal, I get hydrogen and a salt. If I react acid and a metal oxide, I get water and a metal salt. So in this case, I get potassium as the metal because we're starting with potassium oxide. We get potassium chloride. Magnesium oxide, we'll get magnesium salts. In this case, we're using HBr instead of HCl. So we'll get the magnesium bromide instead of the magnesium chloride salt that we saw in the previous examples. We can also dissolve some metals with bases. However, this is a little bit more rare and is pretty much just for the group 13 metals. So aluminum is a great example, where we can take solid aluminum, react it with aqueous sodium hydroxide to make sodium aluminum hydroxide, which is a soluble salt. More commonly with these acid-base reactions, we're going to do some type of titration. So titrations are very useful procedures that allow you to figure out the concentration of some unknown species from the use of a known species. It doesn't matter whether your titrant is known or unknown. It doesn't matter if your analyte is known or unknown. It really depends on what your indicator is going to react with and how you set up your titrant versus your analyte or your solution. So in the case of our lab, we had an indicator that will react with base. And so we want to put that indicator with the acid so it doesn't inherently indicate while in the titrant. Here we have a visual representation of what a titration can look like. So in this case, we have acid as the analyte. We're going to add some base titrant. This is very similar to what we were doing, where we have a hydroxide titrant. We're adding that to some analyte. Once the titrant has completely reacted with the analyte, we reach the equivalence point. So this is what we would call a equivalence point, endpoint. The endpoint is when the titrant indicates. And so the equivalent point is where we have a perfectly neutralized reaction. Now we can start moving into some of the calculations of the chapters. We've done these calculations already. However, now they're in a different format. You have a word problem instead of a lab report. If we're given the concentration in volume of sodium hydroxide, we can figure out the concentration of HCl. This is going to be very similar to our challenge question, except for we'll be using a different reaction. You'll have to predict what the neutralization reaction is, and I will give you a neutralization reaction, so you don't have to worry about that. So first thing we need to do is come up with a reaction and balance that reaction. We have a monoprotic acid to a monoprotic base, so it's just going to be a one-to-one reaction once we have the neutralization. Again, neutralization is an acid plus a base, gives us water and a salt. Once we have our balanced chemical reaction, we want to think about what conversion factors we're going to use to get from point A to point B. We want to start by converting our milliliters into liters so that we can then use our molarity. Molarity is moles per liter. And so ultimately we want to get to moles because we can convert from moles of base to moles of acid using our mole ratios, which is just 1-to-1. Here would be how we would plug in our dimensional analysis, and we would figure out that the molarity of the hydrochloric acid solution is 1.25. We can then go and look at the given information, make sure that everything makes sense in terms of units and magnitudes. If I have way more volume of something and it's a 1-to-1 reaction, the concentration should be lower. If I have way less volume, the concentration should be higher because it's 1-to-1. If it's 2-to-1, 3-to-1, 2-to-3, you then have to do some, fractions in your head, or you can do it on paper. But again, always check to make sure that your answers make sense. We're doing physical things. They should have sensical results. I've mentioned strong and weak acids and bases. It's not going to be something we focus on because we don't have the tools to deal with weak acids or weak bases. Something that is strong fully ionizes in solution, whereas something that's weak only partially ionizes. And we need some extra information, calculations, equations to kind of deal with how much do these things ionize. We're not going to deal with that, so we'll treat everything as a strong acid. If it's a weak acid, we just kind of say, oh, we don't really know. Here's some examples of strong acids. So you'll notice that all of these are monoprotic except for sulfuric acid. Sulfuric acid is the only common polyprotic acid where all protons are strongly acidic. Now, the first proton is always stronger than the second proton, but the second proton of sulfuric acid fully ionizes, where if you take phosphoric acid that has 3 protons, it's a triprotic. Those second and third protons are very, very weak acids. HF is our quintessential weak acid because everyone looks at HF and goes, well, if we look at the energies, HF should be stronger than HCl because the difference in electronegativity is larger. However, because the difference in electronegativity between hydrogen and fluorine is even greater than hydrogen and oxygen, water doesn't have enough strength to fully ionize that bond. And so some of these HF molecules will just float around in solution unionized. This is the hallmark of a weak ion or a weak electrolyte, weak acid, weak base, all the same kind of definitions between strong and weak. Weak things don't fully ionize, strong things fully ionize. So there are a whole bunch of strong acids and weak acids. We want to pay attention to the names. So we point out that sulfurous acid is a weak acid, but sulfuric acid is a strong acid. They're very similar chemicals or polyatomic ions. However, they do have very different behaviors because of the difference in the polyatomic. Here we have SO3 versus before we had SO4. These are all going to be weak acids. Typically, they're either organic acids or polyprotic acids. We could then use this strong and weak acid definition to determine, are these things going to have the full concentration that their molarity indicates, or are they going to have less of a concentration than their molarity indicates? For strong acids like HCl and nitric acid, their concentration of H plus or hydronium ions is going to be the same as their molarity because they're monoprotic and fully ionizable. Whereas acetic acid is monoprotic, but it's a weak acid, so it's not going to fully ionize. So we would say it's going to have something less than its molar concentration. So for HCl, it's just equal to its molar concentration. 1 proton times the concentration by 1, you get the same concentration. Monoprotic, but it's weak, so we just say that it's less. We don't know how much less because we don't have the tools to deal with that yet. If you take Gen Chem 150 or other classes, you'll get that opportunity to learn those equations, but we're not teaching that here, so we'll just say that weak acids are just less than what we would expect, which is why we're just going to treat everything as a strong acid, because saying this is just not very useful. I'll only give you strong acids. HNO3, strong acid, if molarity of the compound is equal to 2.5, it fully ionizes, so its ionized species are also going to be equal to 2.5 molarity. You do the same thing with these. Same idea. Weak acid, strong acid, weak acid. These two are going to have less than their molar concentrations. This one is going to have its molar concentration. We can do the same exact thing for bases. Strong bases fully dissociate. Weak bases don't fully dissociate. We're going to treat everything as a strong base because we don't have the tools to deal with partial ionization. So we're just going to deal with fully ionized stuff. Sodium hydroxide, just like HCl, fully ionizes. Whereas if you had something like barium hydroxide, calcium hydroxide that's a weaker base, it's not going to fully dissociate or ionize. So in the case of ammonium hydroxide, not all of the ammoniums will dissociate. And so we get this weak base type solution. Here's some examples of our weak bases. Again, our weak bases have some tendencies that we don't see with our strong bases. Our strong bases are almost always hydroxide based. Our weak bases are almost always some deprotonated acid or an organic base. Nitrogen, forms a lot of organic bases in organic chemistry. These are weak bases that don't fully ionize in solution, thus the definition. So, same as before, we can look at these, determine whether they're strong or weak, and decide whether or not they're going to ionize or not. Hydroxides tend to be strong. There are some, alkali metal or transition metal hydroxides that are weak acids, or weak bases. But in general, if you see a hydroxide, you can probably assume that it's going to fully ionize. If you see something organic or nitrogen based, it's probably not going to fully ionize. So since we have one hydroxide in this molecule, its concentration is just going to be equal to its molarity. However, with strontium hydroxide, there's 2 hydroxides per molecule, so we're going to have to double this molarity. The molarity of strontium hydroxide is 0.025 moles. The concentration of hydroxide will be 0.05 moles because we have 2 hydroxides for every 1 molecule. We need to double the concentration. This is weak, so it's just going to be some amount less than its molarity. So, just like we said, weak ones we can't calculate because we don't have the Henderson-Hasselbalch or the Arrhenius equations, so we're not going to worry about them. Because strontium is a diprotic base, it can accept 2 protons, we need to double the concentration because of the stoichiometry. More examples. So hydroxides, strong, we're going to need to double the molarity because there's 2 hydroxides per molecule. 1 hydroxide per molecule, strong base, fully going to ionize. It's going to be equal to the compound's molarity. Weak base, it's going to be something less than its initial concentration. That's all we can say at this point, and that's all we're going to do in this class. We already mentioned the autoionization or the self-ionization of water. And so this is what Arrhenius was basically able to observe to come up with his definition, is that he saw that some amount of water was constantly turning into other stuff. And so that other stuff was hydronium and hydroxide. We typically refer to hydronium as H+, but formally 2 molecules of water will react with each other to make 1 cation of hydronium and 1 anion of hydroxide. These will form an ionic pair and will eventually react back to form 2 molecules of water. We call this the autoprotonization, autoionization. We can define this at a specific temperature and pressure. We use atmospheric pressure and 25 degrees Celsius because that's a comfortable about room temperature. At these conditions, the concentration of hydroxide and hydronium is always equal to 10 to the minus 14. At a neutral solution, we have equal portions of hydronium and hydroxide, so they're both equal to 10 to the minus 7. But we can use this equation, or this Kw, this constant of water, to figure out what the concentration of a species is, given that we're not at equilibrium or not at neutral conditions. So if I tell you what the concentration of hydronium is, based on the fact that hydronium times hydroxide is always equal to 10 to the minus 14, you could figure out what the other one was. So given this concentration of hydronium, we could calculate the hydroxide because hydronium times hydroxide will always be equal to 10 to the minus 14. So we could just plug those things in, rearrange, plug into our calculator. We can assume whether these things are acidic or basic by seeing whether the concentration of OH or H+, depending on what's given to you, is greater or less than 10 to the minus 7. If you have an H+ concentration of greater than 10 to the minus 7, like 10 to the minus 6, 10 to the minus 5, 10 to the minus 1, those are going to be acidic solutions because there's more acid, there's more H3O+ or protons than there is hydroxide. But if I have more hydroxide than 10 to the minus 7, there's more proton acceptors than there are proton donors. I'm going to have a basic solution. So that's how we use these type of, equations, the Kw, the autoprotonization of water. We can also relate these to pH, which we will do in a second, but here's just the rest of the calculations for this series. Pretty straightforward. You're just plugging in and rearranging for what the missing value is. You can do the same thing for hydroxide as you do for hydronium, just the opposite calculation, rearrange for a different variable, so to speak. So Neutral solutions will always equal 10 to the minus 7. If it's acidic, we'll have hydronium, which is greater than 10 to the minus 7, and hydroxide, which is less than 10 to the minus 7. For basic solutions, we'll just have the opposite case. For all aqueous solutions at 25 degrees Celsius and at atmospheric pressure, the product of the concentrations will always be equal to 10 to the minus 14. Like I had mentioned, we use this scale to represent acidity and basicity. The common acidity scale is pH. And so the reason we use pH is it would be very awkward to talk about the hydrogen concentration or the hydroxide concentration in some exponential notation. So we use what's called a logarithm to come up with the pH scale. We take the logarithms of the hydrogen concentration to get pH. So that converts our exponential into just a number. Logarithms are an old school technique to convert exponentials to just simple numbers. And so instead of having a scale from, 10 to the 0 to 10 to the minus 14, we have a scale that ends at 0 or starts at 0, depending on how you want to look at it, and ends at 14 or starts at 14, depending on how you want to look at it. We want to make sure that we remember that pH is an exponential type of relationship because these are used to convert exponential formulas. So if I have a pH of 4 versus a pH of 3, pH of 3 is going to have 10 times more acidic molecules in there. And pH 2 is going to have 100 times more acidic molecules than a pH 4. pH 1 will have 1,000 times more. Every number is an order of magnitude. So for every 1 unit, we need to multiply by 10. This is the power of logarithms and exponents. It's why it's very useful in science. It's easy to condense information. Here are the mathematical ways that you'll use logarithms or the pH scale. You're more than welcome to do method 2. This is the algebraic way where you exponentiate the function to remove the logarithm. If you want to do the pure algebra, this is great. It'll give you a little bit better intuition and understanding about, what you're looking at. However, we can just plug into our calculator and use what's called the inverse log function. Sometimes this is log to the -1, raised to the -1 power. This just undoes the behavior of a logarithm. We have operators and we have inverse operators. Inverse operators undo the initial operation. So that's the easiest way to do it. If you're unsure how to do this with your calculator, make sure you ask me in class and we'll go over this. It's very simple. It's, just plug it in a button. Just like taking a square root is just pressing a button. You can do a square root algebraically, but that's a lot of work. Just press a button, have the calculator do the work for you. So we could plug these. pH is equal to the negative log of hydronium concentration. pOH is equal to the negative log of the hydroxide concentration. pH plus pOH always equal 14. Just like hydronium concentration times hydroxide concentration always equals 10 to the minus 14. The way that logarithms translate from exponentials, if we multiply exponents, that's the same as if we add logarithms. So if we add pHs together, we should get 14, whereas if we multiply the concentration of the ions, we should get 10 to the minus 14. Last thing that we're going to really talk about is buffers. Buffers are very important to biological and organic systems. And so what a buffer is some dissolved salt that resists change to pH or to the ion concentration. So typically how we do this is we neutralize some weak acid or weak base that's relative to the pH scale that we're trying to maintain. Once we have so much of that dissolved acid or base that's been neutralized, every other thing that comes into solution that would change that has to go through the buffer first. And so what we do is we'll take some, sodium hydroxide, a strong base, to react with some weak acid to make water and the conjugate base. This base will then resist change to any more acidic solutions. The converse would be taking a strong acid, reacting with a weak base to make another weak acid. So Here we have two different, acidically buffered solution and a basically buffered solution. Bicarbonate is a very common buffer. It's what buffers our body. And so what you can think of is having these buffers in there basically has a spot holder to absorb some amount of acid that would typically go on to do chemistry that you wouldn't want to occur. If you didn't have any buffers in your blood, the second you drank soda that has phosphoric acid and other things in it, it would shoot up the pH, or I guess shoot down the pH of your blood levels, which would then cause a whole bunch of cascading effects, which basically kills off all your cells. If your pH gets too low in your blood, all of your enzymes stop working. If the enzymes stop working, you stop working. So we've talked about a whole bunch of things. Acids and bases have a bunch of definitions. We have some calculations with them. The main thing we want to focus on is the Bronsted definition. So if I donate a proton, I'm an acid. If I accept a proton, I'm a base. The Bronsted definition always works in the case of Arrhenius acids. The Arrhenius definition does not always work in the case of Bronsted acids and bases. We talked about a couple reactions. Those aren't super important. We talked about strong and weak acids and bases. We're going to focus on strong acids and bases because those are the ones that we can fully deal with. Titrations are going to be a big portion of this because we've spent 2 weeks on it in lab. You should be comfortable with this. However, we can also use the self-ionization of water, the Kw constant. Kw always equals 10 to the minus 14 at 25 degrees Celsius in atmospheric pressure. This Kw is how we come up with the pH and pOH scales, which can also be used in calculations of determining hydrogen concentration or considering hydroxide concentration. Buffers are a way that we can resist change to a solution. We typically make these by reacting a strong acid with a weak base or reacting a strong base with a weak acid to form some type of conjugate that resists any more change to that solution. Here's the key concepts. We want to focus on these ones as conceptual topics, mainly focusing on the definition of what an acid and base is. And then for calculations, we have two different subsets. We have calculating hydrogen concentration and hydroxide concentration, and then we have our titrations. The titration calculations are going to be more important. This is going to relate to your challenge question, whereas you might have some multiple choice true and false on pH and pOH. If you have any questions, make sure you reach out to me by email or office hours. Otherwise, I'll see you in lab this week.